our recording. So this is our official start of data structures for today. So thanks everybody again for being patient with the class cancellation on Monday. I think the material that we'll have for this week, it'll be intentionally made it a little bit lighter of an assignment this week. So hopefully it's still be able to complete it on time. But if it does, for whatever reason, you don't feel like you have enough time this week because of the shorter time frame, let me know and I'll give you a couple days extension on that. Another administrative thing is that I have given, so originally I had extended the last week's homework assignment out until Thursday this week, but I've gone ahead and given everybody an extension on that as well until Sunday. So if you haven't completed that, you have more time to be able to ask questions on that assignment as well. And there's going to be no lab this week, no lab assignment due this week, but I'll still be available during the normal lab time tomorrow on Thursday for you to work on the homeworks and ask questions then. So I'm going to go ahead and share my screen. And so the first thing, I have my GitHub issue posted with our just 2 quick baby pictures. There's us at the hospital, and there's the zoom in of the baby crying when he's being measured. And I also wanted to take this opportunity to talk about 2 things related to class and babies. So the first one is that people often talk about the salaries that you can earn as a computer scientist or a data scientist. And we did that at the beginning of our semester, showed you that website levels.fyi, where people sort of share their salaries, and they're all really great salaries, no matter where you work. But one of the things that's less often discussed is the benefits that go along with those positions. And as you may know, in the US, we have no sort of protected parental leave of any sort by the federal government. And California is one of the few states that has some version of parental leave, but even that is pretty minor compared to most other countries. But nonetheless, tech companies, so where you'd be working if you were a CS or DS major, really have very generous parental leave policies, whether you're the dad or mom of the child, and whether it's an adopted child or a natural birth child. So one of the sort of the most famous policies is Netflix policy, where they have a full year of paid time off for both, whether you're the mother or the father of a child. And but if you click this link, it has a link to all the other policies of all the major companies, and the least generous of the policy is 1 month off, with like 3 months off being kind of the average. So I just wanted to highlight that that's an advantage of continuing down this CS-DS path, is not just great salaries, but great benefits at your future employers. I also wanted to mention that, so today is Cesar Chavez Day, and we'll actually be talking quite a lot about that today in class. But first, what this day is it's to commemorate Chavez's work for labor rights. And he was in particular working for sort of the migrant, often indigenous Latino community in California, and working on in farms, agriculture. But it's his work and other people like him that have made these sorts of labor laws that give us the rights that we do have as workers. And I also like pointing out that even though in tech, we have these great benefits and these great salaries, the companies have been illegally colluding to reduce those salaries and benefits as much as possible. And but it's people like Chavez who get us those benefits. Let's see, I think I just already made these announcements about extension on the homework until Sunday, and no lab this week, but I'll still be available during the normal lab time for questions. Let's see, and over here, so for our actual work this week, we're going to be talking about something called Unicode. And Unicode is a way to represent sort of the standard way for representing all text on computers. So whether that text is English language or non-English language. And we'll be talking about, so in English, everything pretty much works exactly as you would expect, but there are some subtleties when working with non-English languages. And we'll talk about those today. And there's a good question in the chat right now about whether there is a homework this week. And there is a homework that will be due this week, and it'll be related to this Unicode concept. But my hope is that it will be a fairly easy, light sort of homework for everybody. So Unicode, it's, again, a system for representing every possible language on a computer, even made up ones like Klingon and Dothraki. They have representations in Unicode. And the system itself has been developed by literally thousands of PhD level linguists and computer scientists. So this is like, it's a lot of work has gone into this. And it's also something that you're not going to fully understand today. In fact, I would say that there are 0 people in the world who fully understand Unicode because it represents all sort of possible ways that humans can express themselves, and nobody is familiar with all of those ways. So we'll just get a sort of sampling of Unicode today, and especially the techniques that you need as a programmer to deal with Unicode. Before Unicode came along, so Unicode was it's about 30 years old now, a little more than 30 years old. And before Unicode, there were some other systems for representing text in computers, and they were always very language specific or country specific. And so the 2 most famous of these, sort of like the 2 original ones, are the English US one, Ascii, is pronounced ASCII, and then sort of the competing Russian or Soviet Union one, KOI8. And this is our English representation of that, but it's actually originally in Cyrillic Russian characters. Unicode also can be used for emoji. It's sort of the standard way of representing emoji. And hopefully at the end of today's lecture, this comic or this comic plus this explanation right here will make sense to you about why it's funny. One last general note is that Python was sort of the first language that had actual good built-in support for Unicode and handling multiple languages natively. So other programming languages you may have heard of, like C++ and Java, sort of the 2 other common languages that intro programming classes use, those have no built-in support for Unicode. And so it's relatively difficult to have good support for non-English languages in those languages. But Python, it's going to be very straightforward. Okay, so before getting into the rest of this, we're going to switch over to our terminals and take a look at some Python code. There's a good question in the chat about, is there a relationship between the words Unix and Unicode? And the answer is actually that they're totally unrelated concepts. So in Unix, the name Unix comes from, it's an acronym for something that I don't even remember. And the unit doesn't have any sort of meaning other than the fact that it was an acronym. In Unicode, the name Unicode comes from the unit stands for universal, and the code stands for code. So it's a universal code for representing languages. The fact that they sound kind of similar is just accidental. That's a good question. Okay, in the, let's see, I'm currently in our week 9 folder, and there is a notes.py file. And this has been uploaded to GitHub, so you'll have access to this after lecture today. But I'm going to go ahead and open that up in the terminal window up top. And you can see that in here I have 3 string variables, and each one of these variables has the same contents, Cesar Chavez, as the three strings right here. And so down here, I'm going to open up Python with the same notes.py. And you can see that if I do string 1, string 2, string 3 like this, we have access to these 3 variables, and they have the same contents, Cesar Chavez. But things are going to get weird. When I do string 1 equals string 2, you'll see that we get false. And if I do string 1 equals string 3, also false, and string 2 equals string 3, also false. That all three of these strings, we say they are semantically the same string, semantically the same, because they mean the same thing, that when a human looks at them, we understand that they're supposed to represent the same string. So when a human looks at them, we understand they have the same meaning. But these are not syntactically the same. Not syntactically the same. And the syntactically the same, we'll talk in detail about what that means here, but that's when you do the equalities in the computer in Python, it's checking for syntactic equality. Are they actually represented using the same ones and zeros internally? And so what we're going to do is see how each of these three strings are represented internally and how we can sort of convert them into a common, what we call a normalized format, so that we can actually compare them to each other and check them for proper equality, check them for the semantic equality. And the first thing that I'm going to do when I look at these strings is I'm going to take the length of these strings. So in Python, just the length function like this to take the length of a string. Like the string 1 has 12 characters, and length of string 2 has 14, and length of string 3 has 13. So each one of these strings, even though they have the same semantic number of characters, they have a different number of syntactic characters. And in order to see what these actual syntactic characters are, I'm going to use the list function in Python. I'm going to convert these strings into lists. And we'll see that when we do that, we're going to actually start seeing some differences between these strings. So I'll do list of string 1. And here, this is what you would probably expect when you did a list of this string. That here we have each one of these characters is a different element, and each one of these characters corresponds sort of in a one-to-one fashion to these characters up here. But the weirdness happens when we look at the other ones. So string 2 like this. And here, well, the first thing you notice that the list is longer, it's 2 elements longer. And there's this weird character right here that comes after the E. What's happened is that in the first string 1, we have what we call a condensed version of the letter E with an accent mark over it. So E accent mark like this. But in the string 2, we've represented it instead of as just one character, E accent mark, we represent it as 2 characters, a normal E plus this special character right here, which means add an accent mark onto the previous character. And if we look at string 3, we can see that string 3 uses both of these techniques, that the first E in Cesar is decomposed into a normal E plus the accent mark special character. And the second A over here is the compressed version of the A with an accent mark. And so the thing to take away at this point is that some characters in Unicode have 2 possible representations. They can either be represented in this composed form or represented in this decomposed form. And it's perfectly okay to mix and match those representations in the same string. There's nothing that says that if you use one representation in one place, you have to use that everywhere.
Hey, Mike.
Yeah.
Is that something that was intentional on like the person who wrote the strings in the first place, or is that just how the computer breaks it down?
Yeah, this is a good question. So this is related to actually how I typed in these characters in the Python file. So yeah, so that'll lead us, that's a good segue into the next topic right here is what are some alternative ways that we can write this same string that we have up here? And here I've written them out in the sort of most human readable form, but there are other forms that you can enter things in Python. And in order to see those other forms, there's a built-in function called Ascii. the Ascii function converts non-English letters into what we call their Unicode code point representations. So I have the function ASCII, and I'm going to call it on str1 like this. And you can see where the letter E should be inside of Cesar, and where the letter A inside of Chavez should be. There are these weird looking backslash XE9 spots and XE1 over here. Instead of just calling the function like this, I'm actually going to print it like this to get this string right here. And if you call the print of the ASCII function, and then you take this and just display it, you'll see that it displays in this form right here. In Python, we've seen this before, where you have a backslash in a string, and that backslash is called an escape character. One of the ways that this has come up before is when we wanted to actually say insert quotation marks into strings, because normally a quotation mark would end a string, but if we wanted to say input a quotation mark like this, a string that is just a quotation mark, we can enter it this way, or we can enter it this way. It's similar with all of these special Unicode non-English characters, that you can either enter them directly by typing them on your keyboard if your keyboard's able to do that, or you can actually represent them directly with the number that represents the character. So here, backslash XE9, like this, is the representation of the letter E accent mark, or it's one possible representation of E accent mark. This command right here, the way it breaks down is backslash X indicates that the next two characters are going to be numbers. So when you have backslash X, and then I'll say ZZ like this, indicates that ZZ are hexadecimal numbers. So each Z is in the range of 0 to 15, and the numbers that are 10 or greater are represented as A, B, C, D, E, F, like this. So this E right here is actually sort of the number 14. And so the two hexadecimal numbers together is all numbers. ZZ can represent all numbers from 0 to 255. Let's see, the particular math of how I'm doing this, of working with hexadecimal numbers and knowing that it maps two hexadecimal numbers to this range right here. This is something that you would cover in the discrete structures course if you take that. And that is a required course for the data science major at CMC. So this is one way of inserting these sort of special characters. This technique of inserting special characters can only work for the first 255 of the Unicode special characters. And so it works for all of Spanish characters, so anything with accent marks or the tilde in, works for French characters. Most sort of European languages can be represented with this backslash X. But 255 characters, that's still not very many. And so there's a lot more that you can represent. And we'll see in string 2 here some of those other characters. So let's do ASCII on string 2 like this. And here you can see that now we have the this big backslash U string like this. And I'm going to print that so that we get access to the version that we can just copy and paste. So if I copy that and paste it here like this, you'll see that this is the sort of nicely printed version of this string right here. If I were to say that equals that, you'll see that this returns out true. Even though these two things are not typed out the exact same way, this these Unicode representations actually represent it exactly internally the same way inside of the computer. And so these two things are semantically and syntactically equal to each other.
What's the difference? What's the difference between when you just did ASCII and then when you did print ASCII? Like, why does one of the backslashes disappear?
Yeah, this is a good question. So let's say, so we talked about escaping quotation marks like this. But what if I really, really wanted to actually insert a backslash? So that's something that is also a valid character that you might want to insert. And so you might try doing it like this. And if I hit enter, you see that I get this syntax error, because here this first quotation mark is opening the string, and we wanted this second quotation mark to be closing the string, but because it starts with a backslash, it's actually just a quotation mark character, and there is no character closing this string out. If you actually want to insert a backslash, you have to do backslash backslash, and this is the string of just a backslash. In order to, when you just display things like this, you see how it continues getting displayed this way in Python. In order to actually print a backslash and just one backslash, you have to put it inside of the print function like this. So print sort of removes these escaping characters. When we called the Ascii function up above, like this, Ascii is returning a string. So it's not printing, it's returning a string, and that string contains the string that you should type in if you want to have the Unicode values exactly. So it doesn't have the Unicode values exactly, it contains a string that you should type in. So that's print, gets rid of those escaping characters for you. Yeah, it is. In general, when we're dealing with these sort of backslashes and escaping, it can be really hard to follow, even for me at times, like what exactly is going on. And so if the details of why it needs to be print ASCII in order to get something that you copy and paste like this, versus if we just did, if we just did the ASCII function like this, and now we copy and paste this, see that we get the same thing out. It doesn't actually do this representation right here. If that's hard for you to wrap your head around, that's okay. Yeah, the main thing so far related to the escape characters is that if you ever see \x, you know that the next two characters are sort of attached to that as one chunk, and it just represents some Unicode character. If you ever see \u like this, this represents also a Unicode character, but when you have \u, there will be 4 numbers following it. All of the z's again are hexadecimal. And so ZZ can represent all numbers from 0 up to about 65,000. That number right there. And so this can represent a lot more range of characters, and basically everything outside of Asian characters like Korean, Chinese, Japanese letters can be represented in this format. Sam, you have a question?
Yeah, do different fonts of the same language have different Unicode?
That's a great question. So the question is exactly how do fonts relate to this? And the answer is that a font is a mapping from one of these numbers onto an image, and that's all it is. So inside of, when you're programming in Python, you never deal directly with fonts. You only deal with these Unicode numbers, and then it's up to the person who's displaying those numbers what to do with them. This actually turns out to be a really big deal, and there is right here. So a font is a mapping from a code point to an image. Each one of these numbers that represents a character is called a code point. And Apple, a couple of years ago, decided to change their font for the gun emoji in order to change the meaning of this emoji, what it means. They changed it from an actual gun to a squirt gun. And this got linguists everywhere furious, because what happened was, we scroll down a little bit. So here's a possible conversation that could have happened. That here's somebody on their iPhone saying, 2 p.m. tomorrow, local park, bring it. And then they send the code point for the gun emoji. And so you're on an iPhone, you see that the gun emoji is a squirt gun. So it's supposed to be like fun and hey, we should go have a squirt gun fight to each other. But everybody else, if you're on Android or Windows Phone or Samsung Galaxy, when they receive that same number, their phones render it differently. And actually, iPhone used to render it with an actual revolver. And so everybody else is now seeing like, hey, bring your gun, we're gonna have an actual shootout. And yeah, so linguists thought that this was a very bad move on Apple's part, changing the font so that the symbol meant something different. But in general, yeah, these fonts are things that are totally up to the user about what to display. Also, so on my, the fonts are also something that are connected to the terminal system that you're using to connect to the Lambda server. So on my computer, I happen to have fonts that have these characters installed. If we scroll down a little bit, I also have fonts for Chinese and Korean and Vietnamese characters and Arabic. You may not have those fonts installed on your terminal system. And so if you were to open up this file inside of the Lambda server, you might see a lot of characters like this. This is sort of the standard representation of when you don't have the font for the corresponding image. If you were to look closely at this, you would see that it contains a bunch of hexadecimal numbers, and those hexadecimal numbers actually represent the code point for this character right here. Okay, so this this character right here, \U0301, is a very special type of character in Unicode. And this character is what's known as a combining character. That by itself, this character means nothing. And instead, it combines with the previous character to modify it. So here, \U301 combines with the E to add an accent over the E. But I can combine this with any other letter that I want. So let's say I wanted to put an accent over an A. I can type A\U301 like this. Whoops. And anytime you use a \U, it needs to have 4 numbers next to it. So I got a syntax error because I only put 3 numbers next to it. I forgot the 0 out front, like this. So A\U301 gives me an A accent mark like this. And I can actually generate any accent character I want. So if I want a Z accent mark, I can get a Z accent mark. If I want a plus sign accent mark, you can see that my font doesn't support the plus sign accent mark. It's a very unusual thing to try to do, but it still is a plus sign accent mark. You could even add it, say, onto like Chinese characters that accent marks are never used, but you can do it. You can represent it in Unicode. So the question then becomes, there's 2 ways to represent a lot of these characters. Let's see. Well, actually, before saying that, there are some characters that have 2 ways of representing them. So like the E accent mark has 2 ways of representing it. We saw, here we go. Here's one way of representing the E, and the other way is \X. What was it, E9? There we go. Like this. So \XE9 and E\U0301, those are semantically the same character, but they're syntactically different characters because we used different syntax in the Unicode expressions, in the Unicode language, in order to generate them. That here we use the combining character, here we just had a single character all by itself. And so here's where, if we were to do this comparison of that, they're not equal to each other, even though they're semantically equal to each other. And so Unicode has built in what's called normal forms. And normal forms are the standard way of representing characters. And so anytime you use a string in any programming language, whether it's Python or something else, you always want to first convert it using a normal form into some standard form so that you can do these comparisons and have the comparisons be semantic and not just syntactic. There are two normal forms that, let's see, there are 4 normal forms in Unicode. There are 2 that we're going to talk about, NFC and NFD. Stands for normal form composed and normal form decomposed. And so the composed version of the E accent is this. This is the NFC version of this NFD expression. And Python has a built-in library called Unicode data, which has a tool for converting into different normal forms for us. So I have string 1 up here. And string 1 happens to be in what's called NFC, this NFC normal form, the normal form composed. And I know it's in normal form composed because it uses this single letter representation for the accent mark characters, for these non-English characters. And what I'm going to do is say string 1 equals Unicode data dot normalize. I'll do NFC of string 2 like this. Oops, so I did my import Unicode data up here, but I didn't actually load the file down here. So let's do that. String 1 equals. And so even though string 1 equals string 2 is false, string 1 equals this big expression up here equals true. That's because this big expression up here converts string 2 into the NFC normal form. I'm going to take this big expression and call the Ascii function on it. And if I do that, you see that, and let's also call the Ascii expression on string 2 like this. You can see that string 2 by itself is in this decomposed form, E with the accent character separate. But when I do the normalize function on it, using NFC normalization, it converts it into this form right here, where the letter is represented by a single character like this. And now when I do the comparison, we get true. So the syntactic comparison becomes a semantic comparison when you make both sides of the equal sign have the same normal form. Here I converted string 2 into the normal form of string 1, but I could also have, say, done string 2 equals Unicode data.normalize NFD string 1 like this, converting string 1 into the denormalized form, the NFD form, and now we get that those two things are equal. In general, it doesn't matter whether you choose NFC or NFD or any of the other normalization forms in Unicode. You just have to pick one and be consistent everywhere in your program. Any questions so far, Sam?
How does the normalize function know what to normalize? Like, how do they know what to convert from what to what?
This is a fantastic question. So this is when those thousands of PhD linguists were sitting down creating Unicode, they were literally just creating this function, or this is like 50% of their work was creating a big mapping of here are all the possible different ways to represent this one different character. And it turns out for the E, there's really only these 2 separate different ways to create them, but there are some characters that have, say, hundreds of different possible ways that you could combine them together. Let's see, up here, for example, so this E has only a single accent mark on it. If we scroll down to where I had this Vietnamese language down here, Vietnamese vowels have a lot of accent marks on them. So this one right here, the A has a hat above it, the caret above it, and it has a dot below it. And so whether there's two combining characters that you can put on there, the hat combining and the dot combining, and you can put them on in different orders. And so there's 4 different ways of representing this character. And as you add more things to the different characters, there become exponentially more ways to create that character. But these normal forms ensure that you are going to, don't have to worry about all of that. Great question. Any other questions so far?
Mike, I'm still a bit confused about the difference between the NFC and NFD. Could you quickly explain that again?
Yeah. So let's take a look just at a single character, this \E9 character like that. And let's do, so ASCII of that, whoops, and spell it correctly with 2 I's like this. So here, when I do ASCII of this character, it just gives me back that same character. And this is what's called the NFC form, or the composed form, because this string has only a single character inside of it. But now if I do Unicode data.normalize NFD, like that, now I'm getting back 2 different characters, this E character, and then this is the accent mark character. So the decomposed form is going to divide things out into multiple characters. The composed form is going to bunch them all up into a single character. Technically, it's a little bit more complicated than that because most combinations of the accent mark character with the E by itself don't have their own composed form that they can be converted into. So if, for example, we have E\U0301, this is the E accent mark, but what about that plus accent mark that we did before? That's a very non-standard thing to try to do. And so there's no composed form of that. If we do Unicode data.normalize of NFC of this expression right here and convert it into ASCII, you'll see that it still stays as this expression right here. But if we did it with the E, it comes down to just a single character. So the composed form, if there is a single character version, it will give it to you. If there's not a single character version, it'll keep it in the decomposed form. The reason there are both composed and decomposed forms is entirely a historical reason. If linguists and computer scientists had our way today, we would only have the decomposed form because that's the most general possible form. But these language standards that, coming back up here, say this ASCII and this COE8 standard and many other standards, Unicode wanted to be backwards compatible with all of these other standards. And in order to do so, they had to add these composed characters as well. Maybe one other sort of general rule of thumb that maybe will help differentiate between the NFC and the NFD form is that the length of an NFC string will always be less than or equal to the length of an NFD string, because an NFC string is combining characters together. So if there are characters to combine together, the length will be smaller. If there's no characters to combine together, then the length will be the same. These are all fantastic questions so far. Any other questions? Okay, then I want to give you just a taste of some of the other weirdness that can happen in foreign non-English languages. So Spanish is about as close to English as you can get from a linguistic perspective, that the alphabet's basically the same except for these occasional accent marks. But Unicode, so you can handle Chinese characters just fine. You can handle Korean characters just fine. These Korean characters are ones where there are many different possible decomposed forms of these characters. A lot of people who don't know anything about Korean think that these characters are similar to Chinese characters, where they're sort of symbolic and representing one character per word or concept. But Korean is actually alphabetic, but that alphabet, the components, the letters kind of get combined together to look like these chunks. And so they have both composed and decomposed forms for all of these letters. Turns out that in Python, you can actually have variable names that are non-English. So this is computo in Korean, computer. And so if you wanted a variable named that, you can do that just fine. And it gives you this text down here. We talked about Vietnamese already. Arabic is a little bit different in that it's traditionally written from right to left instead of left to right. And so on some people's terminals, if you move your cursor in Vim over like this way, your cursor might jump over to the right and then start moving you right to left. My personal preference is to always have these written left to right, just for programming reasons. Makes it a little bit easier. So this is actually, it's a valid Arabic sentence, but it's written backwards, and so very confusing to people who speak Arabic. We talked a little bit about emojis. This German word is an interesting one because of this this letter out here, this thing that looks like a big B. This is an uppercase letter. If we do dot lower like this, oops, sorry, it's a lowercase letter. And if we do dot upper like this, you can see that this B-looking letter gets converted into two S's. And in most dialects of German, this letter right here and the two S's are entirely equivalent to each other. Although some dialects of German, that's not entirely true. But so what's interesting about this letter is that we had one letter that when you change it to uppercase, it became two different letters. And so if we now convert it back into lowercase, you'll see that it goes down to Strauss like this instead of Strauss like this. So for English and for most languages, if you do upper and then lowercase or lower than uppercase, it's these are kind of inverse functions of each other. They'll wash each other out. But for German, that's not the case because of this weird letter right here. This is a really interesting one right here, this numbers variable. If you look at it, it looks like this contains the string 89. And so if you recall in Python, you can convert a string of numbers into integers with the int function. So if we had like int12, that gives us the number 12. But if we do int of numbers like this, instead of giving us the number 89, it gives us the number 47. And the reason for this is that in the language Tamil, it's an Indian subcontinent language, this 8-looking thing is how they write the number 4, not the number 8. And this 9-looking thing is how they write the number 7 and not the number 9. So yeah, just lots of very potentially confusing things like that going on with numbers. Here, so we have two URLs, URL1 and URL2, both going to bankofamerica.com. Let's check to see whether they're equal to each other. URL1 equals URL2. False, they're not equal to each other. And at first you might think we've been talking about these normalized and denormalized forms. And so let's try converting them both into an NFC form. Do Unicode data.normalize NFC URL1. Is that equal to Unicode data.normalize NFC of URL2? And you see that we still get false. And the reason is because these are actually not even semantically the same string. Here in this second string, this B that I have is actually the Greek beta that's been capitalized. And so it's different than the English B, but the font that I have installed happens to display them both as the same character. And so there's no way as a human to distinguish these two things. And so this is a common way for spammers and other types of hackers to try to make you think you're going to your bank's website when you are in fact visiting their website instead and giving them the wrong people your password. So the National Security Agency has this fun document right here about all of the hacking that you can do by exploiting these weird Unicode semantics and changing things like that. It's a interesting read to see some weird edge cases about linguistics and how that impacts user security. I happened to, while I was in the Navy, I happened to work at the NSA for a while, and I can say that these are real things that both people use to attack US infrastructure and that the US uses to attack other people's infrastructure. Let's see. Last interesting one that I wanted to provide was this Arabic character right down here. So we saw before that in English and Spanish, we had like 2 characters that combine together into 1 character. But this is actually an entire, not even an entire word, but an entire sentence in Arabic represented as a single character right here. And so the English translation of this sentence is peace be upon him, what you'd traditionally say after talking about the Prophet Muhammad. And if down here I say peace be upon him, you can see that it's just that 1 character. Length of peace be upon him is just 1. But let's do Unicode data dot normalize. And here I'm going to do what's called the NFKD denormalization scheme. Is that enough parentheses? Yes. And you can see that it's actually 18 characters that have been combined together into 1 character. This is the full phrase right here. And for whatever reason, Arabic happens to have a lot of these sort of phrases combined together down into a single Unicode code point. So the main takeaways now from this discussion are, first of all, that languages are weird and there's sort of no hope of being able to understand all of them in your code. That we've just seen a couple of examples here from like 5 or 6 different languages, and every language in existence, the tens of thousands of languages that people have used throughout human history, have something weird about them that is totally confusing and unique to that language. So you're not going to be able to understand it all. But as long as you do this process of converting things into a normal form before doing your comparisons in Python, then that'll take care of 99% of the issues that you have with foreign languages. The one thing that it doesn't take care of is, so up here we had all of these different Cesar Chavez's. What if we had also string 4 equals Cesar Chavez like this, whoops, spelled correctly like this. So this is how most Americans, English speakers, would type out Cesar Chavez. This is how most Spanish speakers would type it out. And there is no sort of standard Unicode form for converting from this representation down to this representation, because these 2 representations, they're not equivalent syntactically and they're not equivalent semantically. In practice, a lot of applications want to treat these 2 things the same. And so the way that you would do that is you would first convert it into the denormalized form, the NFD form, and then remove all of these combining characters, like the character that generates the accent mark. And that would give you something like this. But we won't talk in detail about how to do that. Just know that it is possible. If you want let's see, if you are thinking about a career as either a data scientist or a computer scientist, this is a blog post that I highly recommend reading and studying. So Joel Spolsky is the CEO of Stack Overflow, and this is his thing about what everybody just absolutely needs to understand about Unicode. In all the classes that I teach, I try to make a big deal about these Unicode issues because they are really, really important in practice. And it's something that, from like the academic perspective, is very, very under taught. That I've looked at a lot of different like CS curriculums throughout the United States, including like top ones, Stanford, MIT, super famous places, and they don't even mention the fact that Unicode exists in their curriculums. It's always just assumed that English is good enough for everybody, so we should just do English stuff. But in the real world, not everybody is just English, and it's really important to be able to handle all of these weird language edge cases. Okay, so the next thing that we have to talk about is what your homework is going to look like related to this Unicode concept. But before we do that, are there any questions about anything we've talked about? Sam?
Yeah, so how do you generate a character in the first place? And how do you assign different Unicode to those characters?
So there's a group called the Unicode Consortium that is responsible for assigning these code points to an individual semantic meaning of a character. And so like, let's say Star Trek, they wanted their Klingon language to have appropriate Unicode characters. And so some people who worked on Star Trek just emailed the Unicode Consortium, said, here's our alphabet. It's got these 50 characters inside of it. And can you please make room for us in your next release about what it will be? And this consortium is, it's made up of mostly professors, but a couple of industry people as well. And it's mostly linguistics people, not necessarily computer science. And they're spread throughout the world. So it's not at all a US-led thing. It's representatives from different language groups around the entire world. And they sort of ensure that there's no like conflicts between when you add your Klingon characters, it's not going to suddenly break Chinese somehow. And so typically it's like a multi-year, maybe like a 5-year process to get new things added. Is that answering the question that you were asking, or is that?
Yeah, it answers my question. Yeah, I have another question.
Go ahead.
So when you select the detect different languages automatically option on Google Translate, does it detect different languages using the Unicode?
Yeah, this is a great question. So for a lot of languages, you can sort of uniquely identify the language based on the Unicode. So like Korean, for example, there's only one language that uses Korean characters. Chinese is a little bit more, you might think that it's just Chinese, but Korean text and Japanese text can use Chinese characters. So the fact that there's Chinese characters, that's a good like narrowing down, but it doesn't 100% do it. And then like if there's English characters, well, there's, I don't know, hundreds of languages that are based off of the Latin alphabet. So you can eliminate some languages that way, but not very many. So they use that as a signal, but then they also use other techniques as well built on top of that. And if after this class you wanted to learn more about language translation, we do talk about that in the data mining class, which again is a follow-up to this class, but is not really a programming class. It's more of a math class, because in order to understand those things, it all boils down to cool applications of linear algebra. And yeah, but so hopefully I'll see a bunch of you in data mining in the future. Let's see, so yeah, for data science specific applications, this Unicode is super, super critical to understand, because if you're analyzing text of any sort, whether it's like tweets like we did in our MapReduce assignment, or whether it is like stock data, anything where text somehow gets involved, it's always going to be stored in this Unicode format, and you'll have to be able to understand that different strings can have the same meaning but be represented differently. And if you're not always converting things into one of these normal forms, then you're going to have think things are not equal when they actually are equal. Okay, so what our homework assignment is you're going to create a data structure in Python that does all of this conversion for you automatically. So to make working with these foreign language strings sort of even easier than it already is in Python. Basically, in our what Python does for us is it provides this syntactic equality, and we're going to provide a semantic version. Python doesn't by default have a semantic version of the string because the syntactic one is more general and it's not quite as efficient in some situations to always do these conversions. And so some programmers want to have this manual option. But by automating this process, we'll learn a little bit more about Python classes and about Unicode at the same time. So first, big picture instructions. We're going to be continuing to work with the same repository that you had last time for last week's assignment. So this is what I called my containers repo, but you should have called it something differently. And this time you're going to be working in a new branch that is not the master branch. So we'll call it the Unicode branch. And so the first steps, same as before, you'll create and check out a branch called Unicode. You'll pull the contents of my Unicode branch into your branch, and then there is this unicode.py file that you have to fix the test cases in, update your README, and you're good. Importantly though, you must not merge your work into the master branch. And so it should only stay in the only in the Unicode branch and not in the master branch. And this again will be important as we go on in future weeks. We're going to be creating this really big repository with a lot of interesting things inside of it, and everything will need to be in its right place. So if you do merge into the master branch and submit with it merged, you'll lose 2 points on the assignment. Also important is that when you submit the link to Sakai of your submission, you need to make sure it's the Unicode branch of the repository that you submit the link to, and not the master branch version. So I'll go over right now how to actually make sure that you're submitting the right branch. So here is the link to my containers repository. And up here, you notice that it's just my username / containers. But then over here, if I click on the Unicode branch over here, you'll see that the repository, the URL up here changes. So it's now has this /tree/Unicode in the URL. And so you'll need to make sure that in the URL that you submit, you've clicked here, gone to Unicode, and submit this version of the web page. And again, this is all to help you get more familiar with the different aspects of how to use Git efficiently. Oops. One other note is that you'll notice that the instructions that I am starting to give on the assignment in terms of what to do with Git, they're getting intentionally more vague. So rather than giving you the specific instructions about how to do this, create and check out a branch, I'm giving you the big picture objective of what you're trying to do. And this is also intentional, trying to get you to sort of refresh your memory on these past things that we've talked about. And in general, in the future, when people are talking about like Git branches and things, they're not going to say, here's the 5 set of instructions to run to do something. They'll just say, create a branch and do this. And it's just understood that you'll be able to do that. So it's 100% okay if you run into issues while you're doing this. That's what the office hours and labs are for, is to help you do that. But that's the motivation behind not giving you the clear, like exactly step-by-step commands to run. Okay, so I'm going to switch back over here now, and let's quit out of the notes.py, and I'm going to go inside of my containers repo. So cd containers like this. Oops. And here on the Lambda server, you can see that I have the, I'm inside the containers repo, but there's nothing here. I think we've talked about this before, but this containers repo is what's called a sub-module of my CSCI 46 Git repository. And a submodule is just a repo that's inside of a repo. So submodule is a repo in a repo. And this turns out to be really important for working on very large projects with, say, hundreds or thousands of people collaborating together. And it, especially if they take up a lot of disk space, like gigabytes or terabytes even. And so I'm just going to real quickly initialize my submodule. Let's see. There's init and, well, okay, I forget the exact command. Most of these Git commands are pretty arcane, and so I always Google them when I need to actually use them. But instead of doing that manually, we'll just look at the actual code through GitHub right now. And it's this unicode.py that we're looking at. And inside of here, there's a class called Normalized String. And this is going to be a string that is guaranteed to be in some sort of normal form, whether it's NFC or NFD. And inside of the constructor right here is where you will be specifying which form it's actually going to be in. And so we saw before that this Cesar and this Cesar, this Cesar and this Cesar, even though they look like they are the same, they may not be the same. And so we can get true and false in some situations. But if we were to wrap this in the normalized string, we would get true and true no matter what sort of representation we're using. There's a lot of magic methods in this class that we haven't talked about yet, so we'll go over those right now. They're all pretty straightforward, and the solution to each one of these functions is, or at least my solution is only a single line for every function. So if you see yourself writing something that's, say, like 5 lines or longer, you know you're definitely going down the wrong track for these functions. We talked about the repr function before. So we already know about that, and the init function. The string function is similar to the repr function, but it creates an actual, something that looks like a string. So if we open up the test cases, which you'll have to do like this. There we go, tests and test Unicode. You can see that here, this strings variable has 3 different versions of Cesar Chavez as the different strings that we'll be testing with. Here is what the normalized strings at the repr is supposed to look like. This is just code. You could copy and paste the string into Python to get back an object that's equivalent. But if you use the string function, string on your thing, it's supposed to look just like it was a string. So you just return the string itself. That's the difference between repr and string. Length just gives you the length of the string. That whenever a class implements this magic method length, you can call this length function on the class. This right here, we say desugars to this right here. Contains is how you do the A and B syntax. So contains does A and B desugars to B dot contains of A. So up here in this expression right here, when it says Cesar in this thing right here, it's calling the contains method inside of the string class in order to see if this is inside of this. It's a little bit confusing because we also saw syntactic sugar for a different version of the in keyword with the iterator. The iterator version is for a for loop specifically, so for x in y. The contains is for when it's not inside of a for loop and it's just something in something else. The get item magic method is for like the dictionary sort of syntax or the list indexing or string indexing. So anytime you have a square bracket b, that sugars into a dot get item b. Because we're trying to be like a list has these lower and upper functions that they're not magic functions, they're just methods for lists. And so you'll need to be able to make your thing go lower and uppercase as well. let's see, we've also seen the iter one. This is one that'll actually take a little bit of, I think my solution has maybe 20 lines of code or so, because for the iter function, you have to actually return an iterable class. And so you'll have to create the class in order to do this. I'm not providing the class for you. This is this is what we covered last week, and so if you want a refresher on this, you can look at the last week's homework assignment and follow the template that I gave you there for what those iterable classes should look like and what their magic methods should be. This last one, the add function, it's just a plus b gets desugared into a dot add b. For these three functions right here, one way that I think a lot of students are going to at first have a problem with is that you want to make sure that these functions do not actually modify the class that you're in. Instead, they return a copy of the class or return a copy of the object. Just like when you call, if we were to say down here in Python and we had our German variable and we say x equals German dot lower, x is, oops, got my lower and my upper backwards again, dot upper. X is the uppercase version of this word Strauss, but this German variable remains as the lowercase, or in this case, the mixed case version of the word Strauss. And so you need to make sure that when you call the lower and upper, you're not modifying your original variable, you're just returning a copy, a new version of the variable. Are there any questions about this homework assignment and what to do? Okay, there's a good question in the chat about in general for Unicode when you're typing in a foreign language or you're copying and pasting them and you enter them into your Python code, are you entering them by default into a composed form or a decomposed form? And the answer is that there is no default, that it depends on your specific keyboard settings and your program configuration, how your terminal is configured, and where you're copying and pasting from. In general, if you're copying and pasting, it's going to keep the normalization of the source, the thing that you're copying from. So if you were to copy and paste this string and this string here into Python, you would, they're in two different normalization forms in the file as is. So in Python, they would stay in two different normalization forms. But if you're typing them by hand, it depends on what your keyboard and your terminal are set to by default. Most applications use NFC as their default. And so most of the time it will be in the composed version, but that's not like a universal rule for various reasons. Other applications use other things. Any other questions about anything? Okay, then that's our official end of class today. Again, I'll be available during office hours right after class now and during lab time tomorrow for questions about this homework assignment or the other one. But if I don't see you then, I will see you next week.
Thanks, Mike.
Thank you, Mike.
You're welcome.
Thank you, Mike. Take care.
Hi, Professor.